So hi Diganta, thank you for joining. So I think the other two people may not be here today, okay? So, but I will complete this thing and we can talk for the record, implementation issues and, after that, it is for them to work on it, okay? I mean, we may want to now and then discuss, or you can discuss separately about the implementation thing. So, yes, so thank you for joining, but we may not have a full body discussion, okay?
Sorry, I couldn't hear you for the first bit there.
Excuse me?
I couldn't hear what you were saying for someone there. I think I have not fully joined it.
Who's speaking?
This is Diganto.
Oh, Diganto, you're very inaudible, okay?
Oh, okay, sorry. Yeah, I'm sorry. This should be better. Is this better?
Yes, this is
Yeah,
better.
yeah.
Okay, what were you saying?
I'm saying I couldn't hear you for the first bit there.
No, I said there will be only Ratnakar joining us today.
Oh.
Nonetheless, in the interest, since we only have a few more classes before the end of the term, actually only what? 2 more, not even 2 more weeks, right?
Yeah.
Only 3 more classes, I think, isn't it?
Yeah, the midsem schedule was given, right? So let me.
Yes. Okay. Only 3 more classes, so I'll have to be pick and choosy about I think 16th, 21st, and 23rd. After that, it is exam week. Okay. So let's get on with it. So whatever implementation issues we just have to discuss, okay, and they can leave it to them to implement it. Okay.
Yeah. Okay. Yeah.
How much we want to have them optimize is something that we have to decide. And after that, it is up to them. Okay. So where was that? So let me share.
Yeah. Sure. Okay. So, yeah. So we should have probably a discussion at some point on this.
We should means who?
Maybe are you available after class? So I just saw this parallelization mail. I think.
Yeah. Okay. No, is that feasible? I mean,
I don't think so. I mean,
yeah.
Not in Python, at least, not with the experience I'm having. I don't think it's a very easy thing.
Okay, so let's not worry about that. I mean, I think we could just have them do something, with respect to generalization. Okay, and
Yeah.
even if they have the basic thing with some generalization, that should be fine. Yeah.
Yeah. Okay.
Okay, so let me directly get on to illustrating the steps of the algorithm. Okay, last time I did say that, I did describe the 2 main phases of property-directed reachability algorithm. One was the blocking phase, in which you identify a counterexample to induction and eliminate them from the current trace. By a trace, I mean the set of frames that you keep by identifying, doing a reachability, one-step reachability check, and strengthening the frames. Okay, so that is one that you do. So you actually remove the CTI by strengthening the I mean negate. I mean adding a clause to each of the frames, which is the negation of the CTI if it is reachable. So that process also checks if a CTI is reachable from F0. If it is reachable, then it will declare it's an error, okay, that there is, the system is unsafe. The other phase, an important thing, is the forward propagation of clauses. And that does relative inductiveness check on each of the clauses that are in a frame and propagates that forwards. And that is important. That's what important to I mean, both from a performance point of view as well as to achieve convergence to a fixed point faster. Okay, and the algorithm terminates when you've reached a fixed point, which is indicated by any two frames being equivalent. Okay. So let's go quickly to the example. And so this is the example I'll use, the same one that I used for the K-induction example. So yes, because PDR works on clauses, the state encoding plays a role. How do you actually encode the states as formula. So let's see. So I'm assuming that the transition relation is encoded, okay, as a formula. So, and for the states are encoded, so there are 7 states. There is also 0, 0, 0, which I assume is a state in which neither P nor Q holds, and it has a self loop. Okay, so P and assuming that we need 3 bits. Okay, we need 3 bits. So this is, and they are encoded in the the way that they are numbered. Okay, so P is the predicate, P, and that is true of states states 1, 2, and 3. Okay, so that is encoded by this CNF formula. Okay, so every frame, every formula here will be expressed as in CNF because SAT solvers work on them. Forget about the new property. And the property here that we're trying to check is Q. So Q is true in all states except uh, 5, 7, and 0. Okay. And therefore, yeah, so that's how I'm expressing. So this is the, so you're able to read it, correct? So I'm showing both the Emacs buffer page and this picture here, okay? Yeah, so that's the CNF formula for that. So you start with F naught. The frame F naught is initialized, is the initial state. The initial state is 1, 2, 3. The initial state is one in which both P and Q is true, the state 1. Okay. Oh, what am I saying? This is, I made a mistake here. It should be just, I made the whole 1, 2, and 3 as initial states. Therefore, all my working will be kind of wrong. But just one moment. My working will be wrong. And this will be a little bit too simplistic. Okay, so let's do this. Okay, this should have been just state 1. Okay, so let's go through whatever I have. Okay, and then we will check what might happen if the initial state was only 1. Okay, so that's okay. So this is encoded as F0. Okay, that's F0 is this formula. So for that example, then how does PDR work? So you start with, every time you start by introducing a new frame. Okay, the first time there will be only F1. So F1 always starts with Q. I mean the property. Okay, the property, because that is the potentially the weakest possible candidate invariant that is strong enough to prove the property, which is Q. So you start with Q, 1, 2, 3, 4, 6. Okay, so those are the states in which Q is true, and that is encoded here like this way in a CNF form. Now, the counterexample to induction are those states that take you out of the frame. So the first not P, that is from F1, F1 is initialized to Q, so not Q. So the states that take you out of the property, so they are what are they, Ratnakar? So in the state
4 to 5 is a not Q edge, 5 is.
Yeah, and there's also 6, no?
Right.
Okay, so that's F1 is always an over approximation of one step image from F0. Okay, so if you start, and that also should all be P states. Okay, so that's why Q state in this case, the property states. That's why you start with Q itself. Okay, so there 4 and 6. So if 4 and 6, the counterexample to induction, are reachable in this case from a preceding frame, which in this case is F0, then you need to eliminate them, or if it is F0, you have shown the reachability. So that's why. So you check if that CTI, counterexample to induction. So first you have to identify that. How do you identify that? In F0, the bad states are the negation of the property. Then you do a check. Okay, if from the previous frame, which is in this case is F0, in one step you can reach any one of the P states, and that's how you get the counterexample to induction for 4 and 6. And that you see if they are in F0 itself, then the system is unsafe, or if they are reachable from any one of the states, even then. Okay, so that's the thing that you check in this case. So and these CTIs are considered as kind of a proof obligation for the previous frame, in this case F0. So 4 is, you ask the question, if 4 is reachable from F0, no. Okay, and then if it is not reachable, then you will strengthen the clauses in this case. They're not yes. Yeah, you end up strengthening them. Similarly, you strengthen 6. Okay, and you also eliminate 6, so you end up strengthening F1 with that thing. Okay, and that's how F1 will be. Okay, that's how F1 will be strengthened to. So we've eliminated those 2 CTIs, and then you move to the next step of F2. So you create another frame. Okay, after you have, so this is the end of the blocking phase. The blocking phase, either it'll identify the CTIs and then checks if they are reachable, and recursively reachable all the way to F0. In this case, there is only one step that it needs to check, that is to F0. And then it will then once again, create another frame to see if there are two-step CTIs still existing, okay? And that's why you introduce a new frame, F2. So every new frame starts with Q of the property, okay? And so that is this one, okay? And then you forward propagate, okay? After the blocking phase, you create a new frame and you forward propagate to see if any of the clauses that are relatively inductive can be forward propagated. So in this case, it'll check if any of the clauses here can be forward propagated, okay? Now, there is a mistake, okay? I'm assuming in the example that I've assumed that all of them initial states, and that's why you got these things, okay? So in any case, so you will, since every state here, you have eliminated these two things, 4 as well as 6. After that, you will see that every clause in that is are inductive, that is relatively inductive. So what does relative inductive checks? Does check, it sees if, assuming that you are in, it checks which clauses in F1 are. For every clause, it does that relative inductiveness check, okay, which is I think I have listed here, isn't it? Relative inductiveness check. The CTI check is if it is reachable. The relative, that's a SAT check, okay, to get CTI formulas. The relative inductiveness check is this, okay? If your current frame implies CI, that is actually, the check is this one. If this is valid, so it is actually for any frame Fi, it is Fi and Fi, that is, it has all the clauses and the relation R and not of Fi is a set of clauses, correct? So Fi is a set of clauses, and Ci, if this is unsat, this is the check. It does. Okay, so which is checking in terms of validity check, this says Fi and R if it implies Ci. And in terms of unsat check, it is the negation of the validity check, which is unsat. Okay, and since here this whole thing, is relatively, every clause is relatively inductive. Why? Because every state, which is the intersection, which is the conjunction of all the clauses, which includes 1, 2, and 3, they fold back into themselves, okay? And therefore, and that happens only if every clause is inductive. That is the intersection, the states in the intersection of all the clauses, they end up going to one of the clauses for every clause. And that's why, after elimination of 4 and 6, you have every clause is relatively inductive, and therefore they get propagated, okay, to F2, the new frame. And that After that, you do the check, okay? If any pair, consecutive pairs of frames in the current trace, if they are in equivalent. As a matter of fact, okay, I mean, you could do it as an equivalence check. The way things are maintained, because they maintain inter clauses, there is also, and since this strengthening and is immediately followed, backward strengthening is immediately followed by forward propagation of clauses, these things are not only monotone in a logical sense, the frames, but they're also syntactically, the clauses are, in Fi minus 1, the set of clauses, would you say, Fi minus 1 is a subset of the clauses in Fi. Okay, that's how it is, except for F naught. Okay, this I'm starting from F1 all the way to do, because of the clausal propagations. You can even do it by a simple syntactic check, because of the way that these things, clauses are propagated and strengthened. Okay, so that's when it terminates. Okay, any questions here? Is it clear how I think what you need to do is do the what are the checks that you need to do, and the essential elements of backward and forward propagation. Yeah. In this case, since all the clauses get propagated, you have reached fixed point in one step. Okay. Let's suppose that if I had F naught as only the state 1, what will happen then? You still start with F1 to be Q. And so that will include, it will be the same set of states, F1. After that, you will still have 4 and 6 to be the CTI. So what will happen after that? So you will ask the question, if either 4 and 6 intersect with your initial state, or if they don't. If they are reachable from the initial state, they don't. Okay. Are you with me?
Yes.
Okay. Maybe you can prompt me a little bit. Okay. After that, what happens? So you will still have,
So it's not unsat.
What is not unsat? So all of them are, yeah. So it is not reachable. So you will strengthen that, and then the same thing happens here as well. Yeah. Because they are, okay, from F1, they are from F1. I mean, it is not unsafe. They're not reachable from F naught, but from F1, it has to be eliminated. Okay. So the strengthening happens there. After that, you will create. Okay. The strengthening still happens. Okay, because they are CTIs. Okay, because they are leading up. The strength, I mean, the reachability check is a check to see if it reaches F naught in this case. It does not. Therefore, that it is unsafe so you determine that it is not unsafe. But since they are CTI, you will still because they are CTI in F1, it will get strengthened, and the same thing happens. Okay, so since you still have all of them that are so they contain all 1, 2, and 3 with 4 and 6 eliminated, and therefore all the clauses will get propagated as well. And so the situation will be the same. So it doesn't matter, okay, whether you make all these states are initial or or not, because you're starting F1 with a P and then eliminating all the CTI. So the way you will have to do is remember that. CTI, how you get CTI is to check if there are states in F1 that gets you out of to not P. Okay, that is at the for every new frame, that is how you identify the CTI. Okay. And so for if there are multiple steps that you will have to do, then the predecessors will become proof obligations in earlier states. Okay, so in that sense, here this thing where you achieve inductiveness in one step doesn't kind of illustrate the recursive nature of strengthening. Therefore, let's look at the second thing. Okay, so where second illustration where I am using this example. It's the same example, so I worked it out here. So it has, unlike the previous example, there's a long chain from a Q state to a non-Q state. So there earlier, this was split, and therefore there was only one step thing. So and there is still the same as far as 0 is concerned. It is a property violating state. So here, you will see that you will need multiple. The blocking phase will require multiple CTI, recursive CTI propagation. So once again, I'm assuming the initial state to be all 1, 2, and 3, but it really doesn't matter. Okay, so in this, the way it works out. So, but that since I have it worked out only for that, let's keep it that way. So you start with F1. F1 will start with Q. In this case, I'm assuming all except 0 and 7 are Q states. And therefore, my frame F1 will contain these clauses, okay, that I'm showing here. This is the negation of this thing. The initial state remains the same as before. So the CTI, the initial CTI, that is the state in the new frame that gets you out of P. So that is 6. So that is not reachable from F0, or neither does it intersect with F0. So you'll have to do both of those things. At each step, you'll have to check if it intersects with F0, because that itself, F0 is not an over approximation. Okay, so that's why you will have to do this special check. You have to do that every time. If the CTI that you identify for a particular I is, if it is inside I, or eventually recursively it is reachable from F0 to do the violation of safety check. Okay, so it is not, and therefore you strengthen. So since it is there, you you strengthen that. So that is in the first step, you strengthen to get rid of that CTI, okay, from F1. So F1 will get strengthened to from Q2 by adding this negation of this CTI, which is the obtained as a result of the SAT check. Okay, and the same SAT check also gives, this is a SAT check from, okay, so that now 6 now becomes, you will have to now check if so, and then you will introduce an a new frame F2, okay, starting with Q again.
Sir, I did not understand one aspect of this process. What are we doing the reachability check for? I understood the counter example checking and the forward propagation part. What's the...
So the reachability check is done, achieves two purposes, okay? One, it is done to see if that CTI is reachable from an earlier frame, from any state in an earlier frame. Okay, this is a new frame. If it is reachable, even if that, so the reachability check is done for two purposes. One is if this CTI also produces another CTI in an earlier frame, okay? Because this one is certainly a CTI. The bad states are either, are states in this over approximation, the counterexample to induction, which in one or more steps reaches the negation of the property. Okay.
Okay.
So when you have the ith frame, what it ensures is that all CTIs that lead to a not prop state up to I steps have been eliminated only, okay, not all CTIs. Okay, so that is one it does. So a CTI in a new frame, that you check if it is reachable from any state in an earlier frame, and that you do recursively. So reachability check does that. So the CTI is like a proof obligation, okay, for that in that frame. So it creates new proof obligations in F2. Okay, so then you see if that is reachable from an earlier frame. So then in that case, there will be a CTI in Fi minus, in Fi minus 1, and so on. Okay, you get that?
Yeah.
So exactly. No, it is, see, instead of, so what it is doing is, you could, if you were to be able to check, in K steps, if there is a K long path, okay, from initial state, if you only maintain F0, since you have maintained over approximations of those things at any particular point, you would have eliminated only, if there are only I frames, one through I, you would have only eliminated CTIs up to I long, okay, in each of the sides. That's why you'll still have, and that's what will be illustrated here, okay? In the previous case, all CTIs were only 1 long, and therefore they just got eliminated from the new frame, okay, that you got introduced, in F1. And then F2, they got propagated, and therefore it was the end of story. Whereas here, in this example, so that is one, to answer your question, okay? So this elimination of CTI is a recursive thing, okay? So it has to, if it is reachable from a if a CTI in Fi is reachable from I-1, then that will create a proof obligation F2. Not only will you have to eliminate that CTI from Fi-1, and then recursively check if that is, if there is in Fi-2, there is something that is reachable to a CTI in Fi-1, and so on, okay? You'll have to do this. And at some point, either this thing gets blocked completely from some Fj less than Fi, but j greater than 0. If so, you know that at least there are no counterexample to induction. You know, I mean, none of the current counterexample to induction that you have eliminated are reachable from the initial state. Okay. So the moment it gets blocked at j, not only, yeah, you would you know, conclude that right now, you know, none of the CTIs that have been eliminated have reached all the way to F0. That is another purpose, okay, that this repeated elimination does. So the moment it gets blocked, the strengthening process also stops at that, okay? Now, the moment you, you know, strengthen something here at any Fi, you will strengthen everything from F1 to Fi, okay? If there is a CTI, say, that is reachable from the previous state, and you strengthen the negation of the CTI in Fi after the check for reachability, in order to maintain this monotonicity, what you do is you will strengthen all the way from 1 to 1 to I, okay? So that's, you know, that's what you do, okay? So that is an additional thing, okay? The blocking phase in the strengthening, you not only you know, strengthen, as long as it is reachable from one of the thing, you will strengthen that, okay? And you will also eliminate that from all the way from 1 to 1 to that, because if it is a CTI in I, it is a CTI in you know, earlier ones too anyway, okay? Therefore, all the way from F1, okay, not F0, because F0 is not an over approximation, okay? So that's how you do, okay? So the strengthening not only strengthens an Fi, I mean the negation, but all the way from F1 to Fi. That proof obligation in I. Okay.
Okay.
Yeah. So I guess I answered. I mean, I said more than I explained more than the thing. So you know what you asked. So the CTI, I mean the reachability, the removal of CTI, extraction and removal of CTI is a recursive process that starts from a new frame whose proof obligation is not P, and then checks if that. So the new frame, the proof obligation is just not P. Then you see, oh, if that in one step, okay, every time you introduce a new frame, its proof obligation is always not P, okay? When you check if that not P is reachable from an earlier frame, I mean the earlier, that is the latest in the earlier trace, then you would have extended checking of CTI for one more step, okay? And if there is one, then you will repeat that, okay, for earlier ones, because that's how you know, you want to do incrementally, okay, with as repeated one-step reachability checks, and that one-step reachability check has to go all the way, okay, until it is blocked at some j. Yeah. Okay, so that is the blocking. Yeah. So in this case, it will be kind of, you know, that repeated thing will be clear. Okay. So here you see a CTI. Okay. So your over approximation, starting over approximation, will have all the states that satisfy the property, which in this case is Q. So it will have 1, 2, 3, 4, 5, and 6. So 6 is a CTI whose witness is one step, okay, to not P state. 5 is CTI of length 2, witness length 2, and 4 is of witness length 3. Okay. Therefore, this is where you will need multi-step blocking phase. So with F1, yeah, I mean F0, the proof obligation for F0 is the CTI that gets you out of to not P thing, and that is in the first one you will identify that it is, in this case it is 6, and it's not reachable from F0 and does not reach F0, and therefore you will strengthen that. That's the first thing. Okay, 1, 2, 3, 4, 5. Okay, now you will have to do forward. Okay, so that is the end of that. Now, I mean, when you have only one, there is no check for thing. You will have to at least have 2 frames in order to do the inductiveness check. Therefore, you will automatically introduce a new frame, F2. Okay, and F2, you'll start with Q, and that's what I've done here. So the proof obligation for F1, this should be 5. I'm sorry, this is 6. This should be 5. Okay, because 6 has already been eliminated. Now, you see, if after introducing new frame F2, and the proof obligation for F2 is not P, you further check if there is something in F1. That is no, this is correct. This is still 6. Okay, this is still 6. If that 6 is reachable, okay, so if that 6 is reachable from F1, okay, and that is F1, which has been strengthened to eliminate 6, you will check if 6 is reachable from F1. It is. So there is a 2-step CTI 5 in F1. Okay, and that needs to be eliminated from F1. Okay, so it strengthens F1. Now, in this strengthening, if there are earlier frames, it will get strengthened all the way from 1 to the I. Okay, the frame I, in which you have introduced, found that CTI. Okay, but in this case, since there is, it's only number 2, so you will have, that is, so there is nothing else before F1 to strengthen it, and therefore 5 gets eliminated. The state 5 gets eliminated here. Okay. Oh, by the way, so to F2, I mean, forward propagation, I forgot. Okay. So, once you introduce F2, before you do the blocking phase, there's a forward propagation step. I mean, if there's only one, the forward propagation, at that point will not hold good. So here, at F2, I should have said, okay, there is a forward, after introducing F2, there will be a check for forward propagation. Okay, that is not Okay, F1 itself, it does not. But here I should have said, I should have done a forward propagation to F2 from F1. There, it'll check which ones are inductive here. Okay, only C1 and C2 are inductive. It would not have mattered there because you're starting with, I mean, they happen to be Q states anyway. You will see that this now has, after strengthening, F1 has 3 clauses. 2 are the original clause, satisfying, that produce Q, and this thing, and this one is not are inductive, and therefore it does not get propagated. Okay, so I think I'm kind of wrong here. Forward propagation in F1 itself, from F0 nothing gets propagated, but when you introduce F2, I mean, there will be a forward propagation phase from F1 to F2. Okay, so in this case, this one is not. I mean, only C1 and C2 are inductive. Why is this not inductive, Ratnakar? This one, 6. This clause is not inductive.
It's not implied by all of them.
It is not implied by?
When you take the conjunction of the 3.
That is true. And why is it that? Because it goes out into 7. See? And 7 is not contained, because from 6, see this clause is saying, what is this clause? This clause is the negation of 6. Okay, a negation of 6 means it will include all these things, 1, 2, 3, 5, as well as 7 and 0. But since a state 5, which is still in F1, goes outside this negation of 6, right? Because 5 itself goes to 6, and that's why, yeah? 5 itself goes to 6, and therefore this one is not inductive. The inductiveness check says at this point the states in F1 are 1, 2, 3, 4, and 5, and this clause is the negation of state 6. So so since 5 is, so that is, it's not inductive, because these states here, they take you out into something that is not in these things, that is not in 1, 2, 3, 4, 5, because from 5 it will go out. Okay, there is a successor state which is out, and that's what this check will do, and therefore it is not inductive. Okay, inductiveness check says that from any of these states, if the negation, if that implies this, this one, or the negation of that thing is okay, this and not of C is what should be, is it unsat? Okay, but that is not the case, because from 5 there is something that goes to 6, which is the negation of this is exactly 6. Okay, so that's why this is not inductive, and therefore what it gives, that does not get propagated, and only F2. I mean, only the original clauses would get propagated. Now, the original clauses are obviously inductive because they are 1, 2, and 3, and they are inductive because that obviously folds back into 1, 2, and 3. Okay, yeah, I mean, the F1 includes 4 and 5 as well, but 1, 2, and 3 is a subset of that anyway. Therefore, you will start F2 with this, which is what you would have started anyway. Okay, and that's how it is. Okay, and therefore then you check reachability. Then you go through the blocking phase. Okay, with the new frame introduced. Okay, so F1, then you see if there is something, the CTI in F2 will be the same as before, because 6 is the state that is leading you out of the thing, and then you check if that is reachable from F1. Okay, and it is, and that is 5. So that is the new proof obligation for F1. So you will strengthen, since that is reachable from, 6 is reachable from F1. So you need to strengthen F1 with that negation. Okay. And that is, you would have checked also if that 5 is reachable in the recursive inductiveness check, if 5 is reachable from F0, okay? If either the initial state contains F0 or is this reachable from F0. So we assume that our F0 in this case is 1, 2, and 3. That's how I worked it out. So from 1, 2, and 3, 5 is not reachable. Okay, that's also the additional check, the recursive blocking phase check does. Okay? And therefore, after you do that, that is the part where the unsafetyness check, and then you have to block in F1 the 5, because it is not reachable from. I'm sorry, you have to you have to strengthen it, because 5 indeed is a CTI in F1. Okay, and therefore that you do. And now you once again create, okay? And you see F1 is not equal to F2, so you still have not reached a fixed point, okay? F1 and F2 has, F1 has an additional correct, yeah. Yes, F1 has been strengthened. F2 is still only a Q, okay? So, yes, okay. So now you will, after introducing a new, so they are not equivalent, and therefore you have not reached a fixed point. So you will introduce a new frame, okay? You will go to the next step, F3. And at that point, as soon as you introduce a new frame, you will have to check if any of the clauses, you have to propagate all the relatively inductive clauses, okay? Now, F1 contains what? 1, 2, 3, and 4. 5 also has been eliminated. So, once again, none of these, only C1 and CT are inductive, okay? Because this check of inductiveness check that I have in here fails, or this unsat check fails for both these two things. Fails there because from, it fails because, for certainly from 4, there is something that goes out to 5, right? I mean, there is not the thing there. Therefore, you will only propagate C1 and C2, okay? And you will have so you will introduce, or does, if one of these clauses get propagated, I have to check, so see, because this one, and no, this one does not have 5. Will not 5 get propagated? So this one has 1, 2, 3, and 4. Yeah, from four, you're getting out, and therefore, certainly this one is not inductive. So this 5 is not inductive. Oh, no, 5 is already there, I think, isn't it? 5 is, so 5 is not even there. And therefore, if 5 is not even there, then it automatically, the negation becomes, the negation of that will become, maybe one of them will get propagated, okay, to F3. So I think certainly the negation of 4, which is this one, does not get propagated. So maybe if this one gets propagated, okay, and then you will get CTI will only be 4, I think. So 4. Yeah, CTI in F1 will be 4, and that will have to get eliminated. Okay, and after that, all of them will get propagated forward, and you will have F1 equals. Yeah, all of them get propagated, and the propagation phase starts from F1, and so all the clauses will get propagated to F2. And then all the clauses will get propagated to F3. What I'm not clear is, maybe one of these things get propagated. You can actually you can actually check that, and therefore maybe then F2 becomes equal to F3. So this is one I'm not clear. You will have to work out the check for the inductiveness check to see if only the C1 and C2 get propagated. Okay, so that is a check, because this one in F1's case will have, let's see, so let's work it out. So let's see if, you know what this thing is, right? This one is negation of 1, 1, 0. This is 6, yeah, which has been eliminated. This is 5, which has been eliminated, right? 1, 0, 1. So from this one, this, when you check if, I think both of them are not inductive, because when you check this will have 1, 2, 3, and 4. From 4, you're checking if you can reach, if every state not of that is 4 and not of this clause, which is exactly 5, is you can reach 5 in the next state, okay, which you can. Okay, so the unsat check says from F1, if the in the next state the negation of this thing is unsat, but that is not true, because from 4 you can reach 5. Now similarly, so here you say from but this one is not even there. So I think this one gets propagated. I'm sorry, because since it is not even there in, so this is okay, this is 6. Okay, so and this one doesn't even have 5. So when you take this and the negation of this and 6 is trivially no. Okay, 6 is, let's see, 6, this and the negation of this. So 6 is not even there, and 6, that is unsat. Okay, so I think one of them will be propagated. Okay, only this one will not be. Okay, so you will have this propagated. I said neither of them will get propagated. So this is indeed inductive. So that gets propagated to F3, but not F2, but not so, but still it is not F2 is not equivalent to that, because F1 still has two more, one additional clause, and then similarly you will have 2 of them propagated to F3. Okay, once it gets strengthened by all 3, 4, 5, and 6, all of them get propagated one by one all the way to F3. Okay, and then all of them will be equivalent. So so that's what happens. Yeah. Okay. Sorry for that confusion. But is the basic idea clear, Ratnakar?
It's clear, but I had one question. Are we, when we are propagating only the clause that are relatively inductive, right?
Correct.
In a previous slide, I think I didn't understand what relatively inductive means, because in a previous slide, you showed that this one you showed that C1 and C2 and C3 implies C1 and C2. That means C1 and C2 are relatively inductive.
No, this is wrong. I explained it in the last lecture itself. I have made a mistake here. Here, what it means is I should actually write this one. Okay, so like what I've said here, this is exactly what you're checking. Or in terms of validity, you have Fi, which consists of C1. I'll put it like this.
No, it's fine. I just saw that the two things were computing different things, so I just got a bit confused.
Yeah, now what I've written here is strictly an abuse of notation. It's actually wrong, okay? That's what I'm trying to explain, yeah? Because what you have is, this is Fi, if Fi contains these clauses, say 3 clauses, what you're checking is if Fi and R of S prime.
Okay, it's contained in the next one. Oh, got it.
So it is this, okay? So that's why I was trying to.
Yeah, I think I got it. Thanks.
Yeah, let me write it anyway. And R of S comma S prime, does that imply okay?
Yeah.
This is the check, which is the same as this. This validity check is the same as the unsat check for the negation. So it becomes Fi, which is the set of all clauses, and R, if that implies the negation, okay, if that is sat, okay. If it is sat, then if it is unsat, okay. So everything in here, that's why I kept saying that, look, in this case, when you had only 1, 2, 3, 4 after elimination of 5 and 6, this unsat check fails. It becomes C2 because the negation of this clause, which only includes this, the negation of this, the clause that used for strengthening to eliminate 4 is 4 itself, or I'm sorry, 5. okay? So that clause, which is the negation of the cube denoting 5, okay, is indeed yeah, so I think the best way to use from 4, 5 is reachable, nah? So this one, Fi and R, which has 4, and the negation of that in the next state, because S prime does contain phi, this becomes sat. Since there is a successor to 4 in phi, okay? Look, the negation of Ci, where the Ci clause is the negation of the cube corresponding to phi, yeah? That becomes sat, and therefore that check fails, and therefore it is not inductive, okay? That clause is not inductive, yeah?
Yeah, got it.
I confuse you more, or
No,
anyway,
no,
this is the check, okay? And that is, yes. So because in here, from these states, a clause which is so the clause that says this particular one, the negation of, sorry, not of 5, of 4, okay, will include 5 also, and that's why it does, okay? It's actually the clause that is the negation of the cube representing 4, okay, which becomes not inductive, because from that, the negation of that, which includes 5, is indeed reachable, yeah? See, it's the clause. See, when you have 1, 2, 3, and 4, that was in F2, okay, before you reached F3. So from there, you're saying if the inductiveness check asks you to check if that implies the negation. I mean, yes, the clause which represents the negation of the cube denoting the state 4, okay? And that the negation of that includes 5, because the negation of state 4, the cube 4, will indeed include 5, and therefore it is reachable, and that's why this unsat check fails, and therefore that thing will not be inductive. All the rest will be inductive. So, and there will be thing, which is kind of a mistake that I made here. Here I said until it became thing, and that is something that you can actually double check. And I think one will be not inductive. One of the strengthened clause that have been strengthened will not be inductive, and therefore F1, F2, F3. Until you reach F3, one of them will not be propagated forward, and therefore those things will not be. In no two FIs will be the same. Okay, it's only after all these counterexamples are eliminated will there be will you get the thing. Okay, so so why don't you review this, okay, with respect to Amstel and work it out, okay? So the to get yourself convinced. There might be some mistakes in terms of what has been propagated, okay? So you will have to check that, okay? And I think I will update this slide, which does not have Okay, there is a mistake here that I will fix. So anyway, so this is the overall code, the pseudo code, okay, which is actually in the book. It's a sequential implementation. Okay, one thing before I mention. So yes, is, see, the way this thing is described, yes, in its simplest form, it will only eliminate one model at a time, okay? So the reachability check at Fi consists of saying, okay, from Fi minus 1, if Fi is the newly introduced thing, from Fi minus 1, if I reach something in Fi which takes you out of not P, okay? So from Fi, is there something that gets you out of not P? Okay, that's the thing. So I have an Fi plus 1. Here I'm assuming Fi plus 1 is the newly introduced frame whose proof obligation is not P. Fi is the most latest frame in the previous cycle. So from that, if there is something that is reachable to not P, that becomes the proof obligation of this. And from, okay, so there are two kinds of, okay, so then you then find, see if there is, that is reachable from that. So you need to find a predecessor in Fi that can reach not P. And that is the model of a SAT check. So, I mean, a SAT check of that reachability check will identify one model at a time. Okay, it will identify the predecessor. And in this case, not P is the CTI in the new frame. If you're doing it for Fi minus 1, it is the CTI in Fi if it is reachable from something. So each time the check itself will give you the predecessor and the and the success. So you will have to not only eliminate, all the CTIs, okay, going from Fi to not P. There are multiple of them. So you'll have to eliminate, strictly in the simplest form, you will have to iterate to eliminate one at a time. Now, that is one place where you could, if you can identify multiple SAT instances at the same time, or that if you can identify multiple models that satisfy the thing, then you can collect them. That is what I call as the generalization step. Okay. Another generalization step is in the predecessor. Okay. That, I mean, that's the same thing. I mean, you will also have to see if there are, yeah. So it is the, yeah. So it's basically multiple things. So once you identify, if you could generalize to collect multiple predecessors that go to CTI, or even in this CTI, if you can generalize the cube structure, okay? If you generalize it to a bunch of CTIs that can be treated simultaneously, that is the generalization step, okay? So you could, before in the blocking phase, especially in the blocking phase, when you identify these CTIs, generalization is the task of trying to get multiple instances, multiple CTIs and its predecessors through generalization. Okay, that is a very important optimization step that is needed in order to make this thing efficient. Okay, so that is needed. Another thing that is needed is because you will be strengthening subsumption check. Okay, so at various points you will be strengthening frames from 1 to I. The moment you discover that the reachability check of a CTI at I from the earlier frame succeeds, then you will be strengthening all the frames from 1 to I to that, to the negation of the CTI. Okay. So, and since the CTI thing works, incrementally at different things, so sometimes you may end up that is one place where you might have strengthened, you might be strengthening, trying to strengthen a frame with a unit clause, negation of a CTI, which is already there. So subsumption check is important, that you, or subsumption checks if a clause that you're trying to strengthen a frame with is already there. Okay, that is also useful when you forward propagate things, so that the clauses will not have any redundancy. So these two are needed. Okay, and what I'm saying is that some thought, if you could give in trying to get you to do some generalization, that will be it would be good. And I expect you to do some minimum form of generalization. Otherwise, what you will have to do is to pretty much implement this sequential thing. And let me quickly go through that. So this is the topmost level. So those are two optimizations, okay? Subsumption checking and generalization. So, and generalization will have to be done while collecting these CTIs in the remove CTI thing. So this is at the top level. All you do here is you initialize F0 to the initial state, get K is equal to 0. P is the property that you're trying to check, the inductive invariant property. If that already intersects with S0, it is unsafe, so you terminate. If not, you will do this repeatedly, okay? So you extend the frontier, you use a new frame, okay? At K is equal to 1. It should be K is equal to 1. Because F0 is already taken. Or this should be K plus 1. Okay, that's correct. Okay. Yes, this should be K plus 1. So extend frontier with K plus 1. What does extend frontier do? It makes the frame Fk plus 1 to be exactly P, the set of states satisfying P. So that's what the clauses in the CNF form of P. And then this is the check for so the first step of the CTI is from Fk, the CTI in Fk, the the latest one in the previous cycle, are states that reach in one step and not P state. Okay, and that's what you will do. S prime is here labeled with not P. That's what it is. So you will compute the predecessor, that is states in Fk that take you to not P. Okay. So, and that you have to remove. So that's what extend frontier does. Now that removal of CTI, and after that, once you have recursive, that's a recursive procedure. So you'll have to go all the way back to potentially back to F0. I mean, if you reach F0, then you have proved unsafety. Or if it gets blocked at some Fj less than K, then you will stop that, the recursion stops there. And after that, you propagate the clauses, okay? So you'll have to remove all the CTIs at every I, all the way until it gets blocked, okay? Or you're proved unsafety. That's when remove CTI terminates, okay? After that, you propagate the, then you go through the propagating, you propagate, and then you do the check. If there exists some consecutive pair in the current trace where two consecutive frames are equivalent, okay? Then you will return success. If not, you increment K plus 1 to extend the frontier. Now, remove CTI. Yeah. So first it checks if the CTI that you produce is itself in S0, because S0 is not an OR approximation. It's exactly identical to F0. That's why you have to check specifically if that state is contained in S0 itself. Okay. If so, then it is unsafe. If not, then you will recursively check the reachability. Okay. So, and this should actually be from 1 to I. Okay. You never change F0. Okay. So this is a mistake. This should be from 1 to I. Yeah, but in any case, here it will, I mean, yeah, it should be 1 to I, because you never modify, 1. But this, yeah. So if the SAT check succeeds at something, which means that CTI is reachable from your, there is a state that gets you to the state, then you will strengthen that, take its predecessor, and then you will remove the thing. Okay, and that's what you do until either it gets blocked or you will end up reaching S0. Okay, so that is what will happen here. Propagate clauses will happen after you have completion of the blocking phase. That is, you have strengthened all the frames as much as necessary. Then you will do this for every I starting from 1. Yeah, okay. So this is the relative inductiveness check. If there in every clause that is relatively inductive will get forward propagated. So Fi plus 1, you will add that clause to Fi plus 1. That you do all the way from 1 to the new frame, including the new frame that was extended. Yeah, so that's how it is. Okay, now in terms of implementation, I think what I'm going to be doing is, maybe in each class from now on, maybe 15 minutes, or maybe we could have some extra tutorial sessions if they need it, okay, to discuss implementation issues. So incremental SAT is something that we'll have to do. Say, as a warm-up assignment, individual assignment, I'm asking you to do, at least each of you, to do one of this. You can pick, okay? This is something that I want you to do in order to ensure, for me and for Diganta, for us, to ensure that you have done some programming. Because the way that you split work amongst yourself, how much programming you do, we don't want to micromanage, okay? But I want to make sure that you have understood the coding aspect of using SAT into doing. So I want you to do individually. You can discuss among yourself and pick one each of these. That you do. This will be a warm-up exercise for how you do things with programming with SAT. The first one is to implement the BMC loop. Input 3 formulas, a Kripke model, a transition relation I, and a property predicate in SMT-lib format, and a number K, which you check if there exists a counterexample of length K or less. And here you should exploit incremental SAT feature of Z3. Implement a program that uses a SAT solvers to find the initial reoccurrence diameter of a given Kripke model. Now, the SAT instance that you will have to check to do this is actually described in the book. Okay, I didn't cover it in the class. Okay, you can actually take that and then you will have to just implement that as a loop which does some repeated SAT call to find a minimal number, okay, D, that's the length of a certain formula, okay, which you'll have to incrementally make it larger and larger. until you find a D that makes a certain formula valid. What formula that you will have to do, just it is something like a BMC formula, is described in a chapter of the book that covers bounded model checking. The other thing is make your BMC complete by adding a K inductiveness check. Okay, I'm saying that each one of you do this. Okay, this is a very good warm-up exercise for you to understand what the things. Then you can actually put these things together and have a complete bounded modulus checking tool that you have written, a K-induction tool that you have written, and a joint PDR tool that you have written, and you can actually run them on common sort of examples and compare how many iterations it takes, what is the performance, and so on. Okay, so this is what is the work for you for the rest of the term. Okay.
Did you tell us that the reoccurrence diameter part we have to?
I described it. I defined what diameter, distance, and reoccurrence diameter was in the class. Okay, and I can point you to. I think that is entitled BMC and completeness threshold.
Okay.
Look at for that keyword. Okay, but what the SAT formula that you will have to use to check incrementally larger until it can be expressed as an optimization problem, computing this reoccurrence diameter as the smallest length of a formula, of a parameterized formula that becomes valid, parameterized with respect to the number of transition relation copy that you have in the formula, just like a BMC formula. Okay? That you will have to incrementally make it larger and larger. That formula that you need to check is actually given, I believe, in the, it is given in the book chapter, and I can even send it to you, upload it, okay? Maybe it is there in the slide that I've uploaded, on the slides, although I did not discuss in class, okay? Yes, so there is an individual assignment and a joint assignment. Now, you should start discussing how you will implement that, for which I have asked Diganta to, for this as well as this, to give as much help as you need, okay? And you should use it, but that should be done outside of the class, okay? That's all I'm saying. And this thing is due by the end of exam week. I can give you one more week if indeed you want to use it, but that's up to you. But it is end of exam week. Yeah.
Also, how's the NSEM going to be? We're going to have a take home, or is it just a project?
I think it's, see, to keep you honest, I don't know. There are just 3 more topics that I'll be covering, okay? One is, and I don't know if I'll have, okay, I would have loved to cover CGAR, abstraction-based inventory, that I will have it or not. So I have a choice, okay? I certainly want to cover reduction of general omega regular safety properties. Now you know how to check invariant checks. Okay, I'm getting to answer you, okay? There are 3 topics, okay, that are not covered, on which I have not given any test at all, okay? Now, I want just some small problems on those things. If you think that it is going to be too much with the programming assignments, I can skip it, okay? But, I'd like to have you, maybe I'll ask questions in the class to make sure that you've understood those 3 things. And those 3 topics are: how to reduce a regular safety property into invariant checking, number 1. Number 2, how to do LTL model checking. Okay, that's basically how you will reduce liveness checking of an arbitrary liveness property, or that, for that matter, arbitrary LTL property, into a check on into kind of a persistence check, okay, or indirectly an invariant check of the negation. Okay, that I complete. There's what is called a tableau method. That is, those are the two topics. And I don't think I'll have time to do Bouquet automaton. Maybe I'll just introduce Bouquet automaton because the tableau method is very much, constructing a Bouquet automaton for an LTL, property, okay, and a transition system to check. So those are the two topics. So what I will do is, maybe this programming assignment itself keeps you very busy. So I'll skip the quiz, but I'll ask you some questions in the thing, and I expect you to maybe actively participate in the next 3 classes, okay, to make sure that you've understood those 3 things. Yeah.
Okay, I was just asking. I don't mind a take-home exam. It's just that if we do have a take-home exam, I think we would prefer to submit our programming assignment a bit later, because this is the same time where we have other exams.
I'm fine. I'm fine with that. I think I can give you another week, okay, beyond the final exam week.
Oh, thanks.
I mean, even a week or 2. Okay. Yeah. Yes. Yeah. Okay.
Yeah.
So I'll stop sharing.
Yeah,
Any other questions? Anything you want to add, Diganta?
No, I mean, I was gonna just say that I think we should probably discuss about the what kind of a generalization could be done in the PDR implementation.
Correct. I think what we should do is, I mean, the 2 of us, you're saying, no?
Yeah, maybe the 2 of us, yeah.
Yeah, I think, well, we can certainly do that just to think. But I think more importantly, after discussing that, we have to come up with something that they will implement, right?
I see.
Is that the goal, or?
I mean, yeah, I mean,
rather than now I've left it open-ended. Okay, I think there is no point in leaving it open-ended because they have enough work between this course and just implementing in other courses. So I don't think we should leave it open-ended. Okay, to be fair, if you want to have them implement something, we should just pick 1 or 2, technique that we understand. Okay, that is maybe given in that paper, and then just define it well, and then just make it. This thing, okay? So what I want to do is, I don't want to do it today, okay? Maybe we can do it, I want us to, I want myself to kind of reread that section, okay, of that paper. And then maybe we can do it tomorrow.
Yeah, sure. So I went, tomorrow.
We went through that. And then if you want to make a proposal, make it, and then we can discuss it.
Yeah.
Or you want to discuss it before?
Yeah, I mean, there are 3. Okay, I'll say some things. There are 3 sort of clever things this paper is doing.
Yeah, just a minute. I mean, I think, does Ratnakar have to be here?
No,
I think he can leave, no?
Okay.
Yeah, thanks. Right, yeah. So I mean, I'll just say it very shortly. There are 3 sort of things that
What are the things there? So let me see. He has something. Look, you can. Okay, one thing is, there's a very simple thing. Okay, just drop. You get a cube. Okay, as a model.
Yeah.
You just keep dropping 1 literal there at a time. Okay. And then see if it is still a CTI.
Yeah. So that is one thing that they're doing. So they're not exactly dropping it. They're calling this ternary simulation sort of a thing. They're saying that, okay, if I have a CTI, and then if I sort of say that, okay, one of the particular.
So let's distinguish. It's always, that's the confusion that I had too. Okay, so every time. See, the CTI check, reachability CTI check is this one.
It is the one that's trying to find something in the previous frame that goes to.
Yeah, see, right in the beginning, it is just not, states, that are reachable in one step to not P, okay? That's right at the beginning. After that, for all frames that are not the latest frame in the previous cycle, there you do this, okay?
Yeah, they're when they're sort of
yeah, this is one point that I did not mention. So they have a not S here, which is really all you have to do. The reason you have not S is because you're going to strengthen it anyway with not S, and therefore, in order to, apparently this is a very so they say why anyway you're going to why bot anyway you're going to you already identified S to be a CTI in that frame.
Yeah. So in any case, like blocking it is a.
Yeah, you're going to block it, and therefore you might as well only do this reachability check for all earlier thing using not S. Okay.
Right.
Now that is one thing that I think I failed to mention. I will mention it. Apparently that gives a lot of thing. Okay, bang for the buck. Okay, in terms of the things, because you are maybe repeated models or something. But now here you will be extracting two things here. No. Even before you do, you'll be the predecessor T is also coming from this SAT instance.
Yeah, so they're talking about this Q2 instance from page 2, right?
Huh?
So okay, so this same SAT instance that they have after like adding block is the predecessor.
No, I'm actually doing this.
Are you sharing screen?
Oh, I'm sorry. I thought I assumed that was shared.
Yeah, okay.